of the Food Authenticity Network, or FAN as I'll refer to it from now on, and it's been supported by 3 government departments, DEFRA, the Food Standards Agency, and Food Standards Scotland. The conference aims to foster knowledge sharing, raise awareness about the importance of food authenticity testing, and help develop global standards and showcase new technologies for detecting food fraud and also verifying food authenticity. So it has a very important role in helping us strengthen food standards, safety and transparency, which we'll be hearing an awful lot about as we go through the next 2 days. Please do take a look at the housekeeping notes, which hopefully you can see in the chat, and they've been posted there. And I'd now like to hand over to Professor Julian Braybook, who's the Director for the National Laboratories at LGC and the UK Government Chemist, to say a few words. Welcome, Julian.
Thank you very much indeed, Lucy, and just let me add my general welcome to everybody online. I think we're in for a very interesting couple of days. So, why is food authenticity actually important? Well, I think we all understand it's a fundamental pillar of the food sector as a whole, and particularly of industry. And it's about ensuring that integrity, the true nature, if you like, of a food product. And that's achieved by confirming its sort of claimed source, its production method, its composition and quality. And it's these things that help maintain industry standards, and by doing that, not only competitiveness of the industry as a whole, but also upholding consumer trust. So, as you might be aware, the Food Authenticity Network was set up a number of years ago now in July 2015. To raise awareness of some of the tools that can be used to help with food fraud prevention as a whole, but also to ensure that the UK has access to a network of expert laboratories using standard type test approaches for food authenticity. And as I said already, this is about effectively giving consumers confidence in the industry and the food that they buy by doing so. So it is my immense pleasure to welcome you to this inaugural Food Authenticity Conference by FAN. And it's my pleasure to welcome our first keynote speaker, Professor Gideon Henderson. Of course, many of you will know him as Chief Science Advisor for UK Department for Environment, Food and Rural Affairs, which is the post he's held since 2019. As part of that, he's Director General for Science and Analysis, and as such is responsible for overseeing the quality of evidence that the department relies on for its policy decisions. And through that, obviously, he provides ministers with scientific advice and sets the priorities for the research and evidence gathering, scientific research and evidence gathering of the department as a whole. He's also Professor of Earth Sciences at the Department of Earth Sciences in the University of Oxford, and a post he's held since 2006. And so you couldn't really have a better speaker to kick us off and provide his keynote speech, looking and sharing insights on science at DEFRA and the government's food authenticity research programme. So may I hand over to you, Gideon. Nice to see you again. Thank you.
Thank you, Julian, and thank you for a very generous introduction. It's a great pleasure to join you today. Let me start by thanking the conference organisers, the Food Authenticity Network, for the invitation to speak to you today, particularly as this is the inaugural Food Authenticity Network conference, as Julian has mentioned, and it's great to see more than 300 of us on the line for this conversation. It's even more inspiring, I think, to see that the network, since it launched, has now grown to be something in excess of 5,000 members in the last 12 years since it launched in 2013, and that membership is spread around the globe. We hope, the organisers and I, that this conference will offer a really great opportunity to hear about the latest technological developments in authenticity research, as well as discussing emerging challenges for the sector and hopefully also identifying opportunities for new collaborations between those of you on the call today. So as Julian has said, I'm the Chief Scientific Advisor and at DEFRA and the Director General for Science and Analysis. It's a post I've been in for a little more than 5 years, and it's my first civil service job in the UK government. I thought it was worth saying just a little bit about my background in this context of this meeting, because my longer term career has been as an academic and particularly as a research geochemist. So I run a lab at the University of Oxford with a suite of mass spectrometers and a trace metal free clean lab. So some of the technologies, some of the techniques that you'll be talking about in the coming couple of days are technologies quite familiar to me, though applied to a different set of problems from those I normally pursue at Oxford. Others of your techniques are much more unusual to me, and I look forward to hearing more about them. It's my job at DEFRA to make sure that the scientific evidence used by our ministers is of the highest quality and up to date. And I do that myself directly. I do it through working through the excellent other scientists that spread across teams in DEFRA, including Lucy, who's chairing us today, and also by bringing in external experts, including some of the people on this call, but also by ensuring that we have the R&D funding and we spend that funding wisely to make sure that we can achieve the research that we need. As a whole, my department, DEFRA, is really proud to put evidence at the heart of our policy making. We use our R&D for 3 things in that context. Firstly, to improve policy making, to make sure that that policy making is informed by good evidence. Secondly, to reduce risks to society and to the economy. And thirdly, to help drive good outcomes, including UK growth. The work of this network, the FAN, really helps us to achieve all 3 of those R&D needs in the government department. It's certainly true that we need this R&D, given the challenges that we face today, many of which, all of which probably are familiar to you, the challenges of climate, of biodiversity, of pollution, a growing global population, and expanding resource needs. And food is really at the nexus of these challenges. We need it, we all need it, and we need at least 2,000 calories of it a day. And there are a growing number of us, now 8.2 billion people on the planet, who need that food. Climate change is making it harder to grow the food, while at the same time that land is limited and needed for other things, including restoration of biodiversity and carbon storage. In that context, it's really important that we continue to keep quality, nutritious food on all of our tables. It's an existential challenge, and it's one that everyone cares about. So that's a general introduction, perhaps, to my role and to DEFRA and the need for food. Let me move on and think a little bit about what it is that makes food security, in particular, such a crucial role for governments. And I'll start by saying that if you look at some of the really major upheavals that have happened in societies through history, civilization collapse, revolutions or famines, those have occurred in times when food systems and food security fail. We're critically dependent on our food system, and we know in the modern that it's complex, with global supply chains transporting food all around the world at all times of year, and with availability of food affected by markets, by global shocks, climate, weather events, pests, diseases, and more. We need the system to be robust to all these challenges, and we rely on this food system resilience, not only so that it supports us and feeds us, but also so that it works with nature to support nature into the future, and with the industry and the businesses, the farmers, the fishers, the food manufacturers that we depend on to provide that food system. We also, and this really gets to starts to get to the point of the FAN, is that we need to be confident about where our food comes from, its quality, and what it contains. And that's all of us. So it's about ensuring that consumers have confidence in the supply chain and in the quality and safety of what they buy. Food authenticity testing and food fraud detection are clearly critical to maintaining public confidence in a resilient food system. And that's what this conference is really all about. Let me quickly return to government business and think a little bit about why it is that we need in the UK a food strategy. DEFRA takes this issue of food security extremely seriously and reckons that food security very seriously and recognises that the way that food impacts our lives in multiple ways. After a pause last year for the general election in the UK, we are again now developing a food strategy, a strategy which will set out very clearly to deliver long-term outcomes to create a healthier, fairer and more resilient system, and to do that very explicitly in partnership with the food system industry to ensure that it works for all. But in that context of a developing food strategy, you could ask, well, what's science got to do with this? What's it got to do with a food system and a food strategy? But perhaps you wouldn't be surprised to hear me as a chief scientific advisor say that science has got everything to do with it and is absolutely critical. In our department, research and innovation is integral in shaping our food system for the future. DEFRA is the 4th biggest government department for R&D spending, and we invest a significant amount of that funding in aspects of the food system. We invest millions of pounds each year, for instance, on R&D to improve the resilience and sustainability of our crops. We use new innovations such as precision breeding, passed into law recently in the UK, to ensure we have the crops we need for the future and to drive UK growth. We're also spending our R&D money on researching ways to reduce the need for inputs such as fertilizers and pesticides, and to improve the tolerance to climate conditions of key plants and livestock, as well as plants and livestock that will look after better our environment, biodiversity and nature. And on climate, of course, we're also working with farmers to decarbonise agriculture, one of the hardest sectors of all to move towards net zero. But DEFRA obviously cannot transform our food system to be fit to face these challenges of the future alone. We need to do that in partnership, and we do it in partnership with many of you on this call. A key research partner at an institutional level that I'll call out is UKRI, and we work really closely with that organisation, co-designing and co-funding important programmes. And these include, just to name 3 of those programmes, although there are many more. But firstly, the Transforming the UK Food Systems programme. This was a strategic priorities fund programme that brings together research to transform the UK food system by placing healthy people and a healthy natural environment together as the goal. So it's coupling those 2 systems together. More recently, the second programme is the Strengthening the Resilience of the UK Food System call. This is funding projects to model potential risks across the food system and to develop interventions to ensure more resilience and that we have a long-term healthy and sustainable food supply. And the third programme that I'll call out is focused on innovation, so the pipeline of moving research towards market. Here we have funded more than 250 projects through the Farming Innovation Programme, FIP, one of DEFRA's flagship innovation programmes. And that work is supporting a wide range of businesses to tackle challenges in the agricultural system and to grow markets and market access internationally. It's through these types of collaborations between government, UKRI, academia, industry, broader stakeholders, no doubt many of you on this call, that we can assure our research and innovation has maximum impact in changing the food system and making sure it's fit for the future. So this is the Food Authenticity Network conference. It's time really that I focus some of my remarks specifically on food authenticity. Now, I'm sure in this audience that you all know what food authenticity is. Broadly, as Julian has said, it's about verifying that the food is what it says it is on the label. And this can be about its geographical origin, it can be about how the food is produced, or it can be about its composition, what are the ingredients that are in it. Now, the ability of people to say food is one thing, but actually put other stuff in the packet has been around for a long time. And we know that food adulteration has been with us since at least the 1800s. The early examples being addition of colours to food, some of which were toxic without making the consumers aware, or the bulking out of products, such as the bulking of flour with chalk. Today, foods that are commonly still reported to be adulterated include herbs and spices, coffee, seafood, honey, olive oil, and actually there are many more as well, but those are some of the most commonly adulterated products. It's difficult, if you look at this as a global problem where food is passed off as the wrong thing, to really quantify the impact of that. But one way of trying to do that, you could try and do it through health or through other benefits. But one way to try and do it is to look at the economic impact of these frauds. And that's hard to estimate, but the best estimates put the annual global trade in counterfeit food and drink to range from something between 6 and 40 billion US dollars a year. It's a very significant amount of trade, which is in products that are effectively mislabeled and fraudulent. To counteract this, government has led the way to keep methods fit for purpose to verify food labelling, so we can really be confident that the label is what's in the packet. And we've been doing this for decades. This research is essential in helping law enforcers and industry to protect consumers from food fraud, and in ensuring that what we eat is what we really think we are eating. The work contributes to a key priority for our Secretary of State in DEFRA, and that's to boost Britain's food security. The work of Food Authenticity does this. It helps to boost food security by helping to ensure that we've got supply chain integrity and to help make sure that that integrity is continually resilient and we have a secure food system. Also by protecting consumer confidence and making sure that there's a level playing field for business. I should stress at this point that our food authenticity research, which I've spoken about and will say more about, is not just done alone in government. It's done in close collaboration with our colleagues in other government departments, and particularly those who are co-sponsoring this meeting, the FSA and Food Standards Scotland. And I'm delighted that you'll be hearing more from my counterpart, the Chief Scientific Advisor in the Food Standards Agency, Robin May, in his keynote address tomorrow. So now let me switch gears a little bit and talk about just a couple of specific highlights from the work of the government's Food Authenticity Research Programme. And again, there are many examples that I could pick on here, but I'll pick on a couple of case studies from the programme. I hope you'll hear many more examples in the coming 2 days. The first one of those that I'll focus in on is DNA testing, and particularly with relevance to the horse meat scandal. In the 1990s, when issues about adulteration of fruit juices really hit the headlines and became a media story, the FAN programme really helped the community to develop the DNA methods that we needed by adapting forensic science, and then we could adapt to check for food fraud, particularly in the first instance around fruit juices. These DNA methods, though, have now been embedded and have become a mainstay tool. So in the decades since then, they've become extremely widely used. And they've led to pioneering work to detect and combat other cases of food fraud. Just some of those are the mislabeling of durum wheat in pasta, mislabeling of fish species, and the high-profile case of the mislabeling of horse meat in beef. That incident, the horse meat incident, hit the headlines in 2013, and that it was discovered that undeclared horse meat was found to be present in really quite a lot of different beef products across consumer choice ranges. Consumer trust was damaged as a consequence, and DEFRA government required a reliable food testing approach to address this trust issue, and also to ensure more broadly that horse meat was just no longer surreptitiously getting onto our shelves and affecting retailers and consumers' confidence. DEFRA, working with the FSA, jointly commissioned an official UK survey of beef products to look for undeclared horse meat. And that survey work, was fundamentally underpinned by DEFRA's research to scientifically quantify food contamination. It lent very directly on the history of research into DNA tracing, enable us to ensure that real-time PCR could be used for the detection of equine DNA in food samples. And by so doing, we were able to develop a qualified and standardized technique to provide a real gold standard for testing of horse meat. Since then, since that first work, we've worked with the European Committee for Standardisation, particularly their Authenticity Technical Committee, and published a BSI and European standard for a DNA-based method for quantitative detection of horse meat. This is really a significant achievement, and it's the culmination of a huge amount of collaborative work which led back to early development of novel techniques and then their application to an important problem, and was done in collaboration with LGC and with the Food Standards Agency. So standardization of analytical methods such as that example help to ensure that laboratories have a harmonized approach to food analysis, and that we can have confidence in testing results from labs across the country and the continent. And you'll hear more about this tomorrow as we look at some non-targeted DNA work and some approaches such as next generation sequencing and DNA metabarcoding. So my second case study that I'll talk about after that DNA example is in a scientific territory slightly more familiar to me as a geochemist who applies isotope tools to some of my problems. And this is the application of stable isotope ratio analysis to determine food origin. And this example is to focus in on the verification of origin. It's sometimes very hard to work out where foods come from, but it has been a key theme of the Food Authenticity Programme over the years. Verifying the geographic origin is challenging, and the best way to do it often is to establish a significant database to give us a reference sample set against which we can test claimed location of new products to check the analytical data is consistent with the reference data set. One approach to this is to look at stable isotope ratio profiles of foods, and particularly sometimes combined with trace elements analysis. These chemical markers can be characteristic of the local environment. The oxygen isotopes, for instance, reflect the rainfall composition, while carbon isotopes and trace metals reflect the local soil composition and underlying geology, so they're place-based aspects. Earlier projects commissioned under the Food Authenticity Programme have looked at establishing this technique for British beef, for poultry and for eggs. A recent example is to use it, as has been announced in the media, to trace grain from Ukraine. And this work's enabled us to track grain stolen from occupied areas of Ukraine and to trace it in Russian shipments. DEFRA has worked with Ferroscience Limited and with World Forest ID to develop a geographical database across key areas of Ukraine to establish the isotope and trace element signatures that the place and the grain has from that area. This data from a now extensive grain reference sample is combined with machine learning models and used to predict isotope signatures from specific locations. And combining those tools means that we now understand the chemical signatures of grain from nearly 3,500 locations. This will enable us, and is enabling us and the Ukrainians, to be able to compare grain that they suspect to have been stolen against those within the database, and to determine the origin of the sample. This work, this tracing of the food location and the location of growth, will strengthen in the long run the food security of Ukraine and ensure the country remains a major supplier of agricultural products worldwide. The recent review of methods for origin verification, I understand, is something that Ferro will talk more about later today, and one of the highlights of work to come is to overcome challenges in this area. Remains a very complicated problem to verify origin. This is also an area in general where, because the size of the data sets are large, novel technologies, including AI and blockchain, will probably help us to address challenges in the future. So I'll start to draw to a close now. I think I'm probably just about out of the allotted time, but I'd like to make some comments in closing about the Food Authenticity Network in particular. This network that hosts the conference today, of course, was set up with funding from DEFRA in 2015, and it was really in direct response to the horse meat scandal that I talked about earlier, and particularly in response to the independent Elliott review that looked into that horse meat incident. That review highlighted that we needed better access to laboratory services, and we needed to use standardized and validated approaches to testing. That's why we're here today, to recognize the achievements of the network already in achieving this goal, and to work and to recognize the excellent institutes and individuals who make up that network. In the next 2 days of the conference, many of the projects you will hear about have been supported by DEFRA, by FSA and Food Standards Scotland, but delivered, of course, in partnership with all of you. I'd like to just highlight a couple of the areas in particular where this work is ongoing. This includes seeking to understand authenticity risks around novel foods, including those derived from alternative proteins. It includes development of non-targeted approach to detect potential mislabeling of meat species. And it includes continued use of isotopic approaches to verify origin. And these are the types of approaches that will continue to ensure that we can give consumer confidence in food and where it comes from, such a critical element of our food security. We really seek to maintain that confidence, and we'll do so best by applying science-based verification technologies. As new technologies emerge in this area, it's critical that we continue to innovate and to bring new approaches and new technologies to bear on the problem. I know that many of you on this call are working on just those sorts of areas, and we thank you for your efforts. Today's conference is also a great example of collaboration, bringing together the 3 sponsoring organisations with the whole of the membership of FAN to share our knowledge. In that process, I thank you greatly for all the expert work that you're doing to ensure that all in the UK can trust that what we eat is what it says it is. Thank you very much.
Thank you, Gideon, very much indeed for sharing your insights and thoughts about the importance of science, of DEFRA, and also your reflections on the Authenticity programme. It's been most insightful. I'm very thankful for your comments, and I know that you have to go now, so thank you very much for joining us today. Much appreciated. Bye. Okay, so I can see we've got quite a few new joiners since we started now onto the call. So it's just to remind folks, if you've got any questions for speakers, to put them in the Q&A channel, and we'll be dealing with them towards the end of today's session. And there's a chat link there to further reading list that includes projects and initiatives that might be interesting for you for today, that you might find useful. So do have a look at those and do pop in any suggestions. So we have a very busy agenda this afternoon. So if I could just ask our speakers to please keep to your allotted time of about 25 minutes. If I think you're looking like you might need to go over, I'll give you a 1-minute nudge just to get you to try and to wrap up, so we can hear all the talks we have today. So great. In that case, I think we can now move on to our next speakers, which are Sophie Rawlinson, who's the Food Authenticity Programme Manager at DEFRA, and Bhavna Palmer, who's a Senior Scientific Methods Advisor at the Food Standards Agency. So Sophie and Bhavna, over to you. You'll be providing an update for us. So let's hand over to, I'm not sure if it's Sophie or Bhavna first, but over to you. Thank you.
Thank you, Lucy. It's me first, so I've just tried to share my slides. Hopefully you can see those. Yeah, that's not good. Thank you. Okay. So yeah, thank you. I'll just start by saying thank you for the opportunity to present today. We're very pleased to be supporting this inaugural FAN conference. So my name is Sophie Rawlinson. I work in DEFRA, in Agri-Food Chain Directorate, managing our authenticity research programme. I'm just going to give a bit of an overview of the work we do under the programme at DEFRA. I'm doing a bit of a double act today with Bhavna Palmer from the Food Standards Agency, who's going to talk after me about the work they do at the FSA on authenticity, as both departments have an interest in this area and we work really closely together. So I was just going to cover why we have a programme on authenticity at DEFRA and give a little bit of detail about the legislative context for the work and the programme's aims. I'll talk a little bit about the structure of the programme, the type of work that we fund, and then pick out some recent highlights from work that we've commissioned. And I was just going to finish up with some reflections on some of the sort of current and future drivers that might be impacting on food fraud and food misdescription, and then some of the technical and scientific challenges that we will be facing in the future. I think the idea is to sort of set the context for the more detailed technical discussions that you'll hear later on in the day on DEFRA and FSA funded research, as well as other research as well. So in terms of the aims of our authenticity programme, so what we want to do is to try and develop fit for purpose tools and methods to verify food labelling and compositional standards rules. So the aim really is to support enforcement of food law with these testing tools and to make sure consumers can have confidence in food labelling. And then as our keynote speaker already highlighted, this contributes to DEFRA's priorities around supporting Britain's food security, so making sure we have supply chain integrity and a resilient and secure food system. And the work we deliver closely in collaboration with others, so our contractors, our expert committees, and a range of stakeholders and other departments as well. So as I mentioned, the programme focuses on methods to verify food labelling rules. And there are various pieces of legislation that DEFRA leads on that cover how our food is labelled and compositional requirements as well. These rules are there to maintain high standards on the information that's provided to consumers, so consumers can have confidence in the food they buy and make informed choices as well. So there's minimum quality requirements for certain key commodities which are set out in law. So for example, things like meat products, bread, fruit juice and bottled waters. And then food information to consumer rules cover sort of general labelling requirements, so things like where food was produced, the ingredients list and the name of the food as well. And then there are also specific marketing standards around some products like beef, olive oil and poultry, marketing standards that cover food that's labelled as organic. And then also the UK Geographic Indication Scheme, which sets out specifications for products where they have a protected name that's linked to their geographic origin. So given this legislative context, I was just going to give a few examples of sort of food misdescription that we might come across and have seen in the past. So examples might include claiming the incorrect origin of a product, so claiming something like beef from South America where it's labelled as British. It might be adulteration with another species that's not declared on the label. So, for example, adding chicken or other undeclared species to a lamb kebab. There might be wholesale substitution of a product. So, for example, bassa, a fish which is sold as cod or haddock. And a common one is sort of dilution of a product, usually with water. So it's bulked out. Things like shellfish and meat can be bulked out with added water. And I think products that are from a particular geographic area or produced in a particular way can obviously attract a premium price, which increases the incentive for food fraud and food mislabelling as well. So the work that we commission under our programme really falls into three main themes. So we have projects on method development, so this is developing tools or looking at existing and new technologies and how they can be applied to address food authenticity issues. So we might be looking for reliable markers of adulterants, commissioning feasibility studies to test that method works in a real world scenario, through to validation and optimising methods to assess if they're fit for purpose. We also have a lot of projects that support knowledge transfer. So once a method is developed and validated, we want to roll it out to laboratories so that they can take it up and use it. So our knowledge transfer work covers dissemination activities. So for example, producing and publishing standard operating procedures for methods we've developed and training and upskilling labs to build capability so they can respond to any future food fraud incidents. We also have a number of activities around harmonisation and collaboration to make sure we've got a joined up approach globally to respond to food fraud. So we undertake a range of horizon scanning activities, and the programme is informed by these and by surveillance and sampling data as well from the FSA. And we're also supported by two expert independent scientific committees our authenticity steering group that advises on the strategic direction of the programme, and our methodology working group, which assesses methods developed under the programme and gives technical advice. So just going to give a bit of a snapshot in this table of some of the current and recent issues that we're interested in under the programme, focusing really on methods here rather than specific commodities. But we're currently interested in looking at mass spec-based methods, peptide mass spec and ICP mass spec, for looking at detecting undeclared offal tissue in meat products, using both peptide markers and trace metals as a screening and confirmatory analysis to detect undeclared offal. We also have a number of projects looking at database fitness for purpose, so addressing some of the scientific issues around honey authenticity testing, and we're developing some work to look at how you can assess databases to make sure they're fit for purpose, and how you can have standardized sampling protocols as well. We're also interested in projects around looking at new digital data traceability tools, blockchain distributed ledger, and how they can be applied to verify origin and traceability, initially looking at quite simple supply chains to assess how feasible that might be. And we also have work looking at next generation sequencing, which offers a lot of potential for food analysis, really to make sure that we can set some performance target standards and best practice advice for how NGS methods can be applied and validated. And then we've already heard sort of mention of alternative protein and novel foods, and I think here we're going to need a range of different approaches, so genomics, proteomics and metabolomics, and possibly other approaches as well, to look at potential fraud risks associated with these types of products and develop fit-for-purpose methods to test those. I think we still need a toolbox of techniques, so we know that different methods are suited to looking at different authenticity issues. Some approaches are more mature and well established than others, so obviously like DNA-based speciation methods are well established now. But the techniques that are out there range from sort of more complex chemometric modelling type approaches through to simpler, maybe microscopy-based techniques. And we also have some approaches that are better suited for screening for a particular authenticity issue that may have a high degree of uncertainty associated with the results, through to confirmatory methods that are well validated and standardised and for which labs are accredited. So just going to highlight a couple of pieces of work under the programme in each of these themes. So in sort of method development, tool development theme, we started work quite a few years ago on looking at peptide mass spec approaches to look for species-specific markers in meat to allow us to verify meat species labelling in products and detect adulteration, ideally with a multi-species screen. So this is a really nice example of a piece of work that was developed initially on a high resolution platform and then simplified onto a platform more suitable for high throughput routine use. So we went all the way through the sort of pipeline from horizon scanning to look at what tools might be available, developing and optimizing the method, validating it through an international collaborative trial. And then about 18 months ago, we were able to fund a training event to roll the method out to interested laboratories, alongside a method to look also for gelatin detection on the same platform. And the work's now being discussed at CEN for potential standardisation. In terms of knowledge transfer, we were able to put in place a joint collaborative co-funded knowledge transfer programme delivered by the government chemist and supported by FSA and FSS, which has allowed us to put in place a sort of longer term, more strategic approach. So we have the flexibility to respond to emerging issues and reach a wider audience with a range of activities. So things like e-seminars and webinars and workshops, providing tools and the know-how to respond to current and emerging analytical needs. We've also done a lot of work on developing best practice guidance under the programme on specific technical issues, from sampling guidance through to guidelines on nitrogen factors, and then more recently the weight of evidence toolkit, aiming to support a weight of evidence approach where there's no single confirmatory method available. We also continue to support the Food Authenticity Network, and a key achievement recently has been to work with the Centres of Expertise on the network to establish a framework for how we'd work together, or how they would work together to advise government in the event of a significant food authenticity incident. And we were able to stress test that with an exercise last year. And then the last highlight I wanted to give was around harmonisation, really, and a lot of the standardisation work that we've been able to support over the last few years. So we've really been able to increase our input and involvement in a SEN technical committee on European standardisation, to support standardisation of methods and disseminate methods, some of which have been developed under our research programme. So we support UK experts to lead on 3 SEN working groups, one on concepts, terms and definitions, one on mass spec methods for authenticity, and one on spectrophotometric methods. And work led by FERA under Working Group 1 resulted in the publication last year of a standard defining food authenticity and food fraud terms and concepts, which is a really nice output for that working group. And I know we've got a talk tomorrow on some of the benefits of internationally harmonised standards, which would be interesting to hear. So I'm now going to pass on to my colleague Bhavna to run through some of the FSA's work.
Thanks, Sophie. And yeah, thanks to the conference organisers as well for inviting me to speak. So I'm Bhavna Palmer, and I'm the Senior Scientific Methods Advisor at the FSA. I work in a team that deals with sampling, laboratory policy and methods. And today I'm delighted to give you a brief overview of the work that we do in the team and at the FSA. And I'll finish off with some of the research that we've completed on authenticity. So to start with, just a brief background on who the Food Standards Agency is, if you don't know. So we are a non-ministerial department, and we're responsible for safety and hygiene regulations, and also food safety labelling. And that's important, and I'll talk about food standards labelling in the next slide. So we work with the local authorities to enforce food regulations, and we provide risk assessments to support authorisation of regulated products. Now, we also have a National Food Crime Unit sitting within the FSA. Now, this is a UK-based team that looks at serious food-related crime, and which includes food fraud, adulteration and misrepresentation. And in Scotland, food safety, hygiene and nutritional standards are regulated by the Food Standards Scotland, and food fraud there is supported by the Scottish Food Crime Unit. So, and they work similarly with the National Food Crime Unit. So the FSA's mission is food you can trust, and we do this by ensuring that food is safe, food is healthier, more sustainable, and food is what it says it is. And our commitment to food authenticity and food fraud is based around this final vision of food is what it says it is. So as Sophie mentioned, we have a strong partnership between the FSA and DEFRA in tackling food authenticity challenges. And DEFRA lead on the food standards regulation and compositional labelling policy. And the FSA is responsible for enforcing those regulations. So it's really important that we work together. And then in terms of engagement, and again, Sophie mentioned that there are 2 groups, DEFRA Authenticity Steering Groups and the Methods Working Group. And members from the FSA Science Team and the National Food Crime Unit sit on the steering group and the working groups as well. And we're also joint secretariat for the Authenticity Steering Group. So there's a lot of interaction and, collaboration there. And also in terms of research, we do collaborate on research and standardization activities. And we also joint fund the initiatives such as the Food Authenticity Network and the Knowledge Transfer Programme that Sophie mentioned. So our authenticity work is covered within these 3 main areas. So that's sampling, methods research and lab capability. And each of these feed into one another. Now, with sampling, when we do sampling, there may be gaps identified in methodology, and this feeds into our research program. So that way we can review and develop and improve any methods that need developing. And once we get suitable methods and approaches, we can transfer these into our official laboratories. Now, these are our national laboratories that are responsible for doing enforcement testing. And it just helps build their capability as well. And with better capability, we can support the sampling that we do within the FSA, as well as the enforcement activities in the UK. Now, this integrated approach helps the FSA to detect emerging risks and improve food standards, and also take action against food crime. And I'll go into detail on each of these areas now. So for sampling for authenticity, so FSA carry out regular sampling, and last year we spent around £3 million on food sampling activities. And one of the priority areas for sampling is to check that food is authentic, and sampling for authenticity is undertaken under different sampling programs. So we have our retail surveillance survey, we have the grant-funded targeted sampling by the local authorities, as well as the OPSON program. Now, the OPSON program is an operation which is a sort of a joint initiative between Europol and Interpol, and it targets fake and substandard foods and beverages. And our food crime unit annually support and fund sampling to support the OPSON program. But in terms of the annual retail sampling survey, last year, about 40% of our samples were taken for authenticity purposes. Now, they sampled across the range, but about 40% last year were for authenticity purposes. And this could be range from labeling and sample testing. So, and out of that, we found that about 97% were found to be satisfactory. In fact, I've got down those 2 years there. So in the last 2 years, most of the samples taken were satisfactory for authenticity. And the types of commodities that we've tested over the years include meat speciation, burgers, herbs and spices, oils. So there's a whole range of commodities that we sample, and they are sort of targeted sampling programs as well. So any sort of non-compliances or unsatisfactory results are shared with the local authorities and industry stakeholders. And they also go to inform our food crime unit strategic assessments, which is published as well. So moving on to official laboratory capability. And again, these are our national laboratories that do all the enforcement testing for us. So our sampling and research program have direct impact on laboratory capability. And to improve capability and also, to prepare food systems for the future, the FSA has invested in a laboratory grant program, and that's been going on for a couple of years now. And this just ensures that laboratories have access to suitable testing methods. They have qualified trained staff working in the labs, and that the methods they use are accredited. And basically, UK laboratories should have good quality assurance so that we can be confident in the methods they're using for enforcement purposes. And it could be in the authenticity area or any other areas as well. So, this way we're investing to build their capabilities to help the UK enforcement system. Right, so moving on to methods research program. This is something that I lead on at in the team. Collaboration with DEFRA and wider stakeholders has been really important to ensure our research program remains relevant and adaptable to emerging risks and technologies. So we get ideas from wide stakeholders, the national reference laboratories that we have, official labs, internally with our policy teams, and we get ideas for our research program there. But the program actually supports many areas in the FSA, as well as our strategic objectives and the areas of research interest. So our interest directly impacts the advancement of authenticity methods. As Sophie mentioned, there's a lot of research happening there, and outcomes can be used to influence standardization activities in Europe and internationally. And all our reports are openly published and can be found on the FSA website. So our research has included areas such as horse meat, speciation, reviews of methods for herbs and spices and country of origin, as well as developing new methods for honey authenticity and looking at rapid screening point of contact devices as well. And in terms of spend, over the last 4 years, just under half of our R&D budget has been invested in food authenticity research, and over a quarter on allergens and other areas such as novel foods and genetic technology. Okay, so now I'm just going to share some of the recent examples of the research that we've been doing. So we've conducted a couple of reviews of authenticity methods. Now, I suppose this is mainly because in some cases there is no one single definitive method to help us identify authentic food. And this is the thing about authenticity. It's really quite challenging to get that, all singing, all dancing methods. And rapid screening methods are increasingly being used for initial detection of authenticity and fraud. Most of these methods are non-targeted, which means that they look at the entire sample composition rather than a specific compound. So these methods may help us identify suspicious samples, but interpretation of results from non-targeted methods can be challenging, and they require the use of reference databases. And you heard in Sophie's talk about the work that we are doing on databases. So looking at the first case study, this was a review of herbs and spice methods. And through our retail surveillance program, we identified a gap in capability for screening herbs and spices. So currently the method used in laboratories is microscopy. It's a good enough confirmatory method, but can be quite time consuming for a laboratory. So we went about with commissioning a literature review and a stakeholder engagement. And this was conducted by Laboratory of Government Chemists, LGC, and Queen's University, Belfast. One of the recommendations that was made was the application of rapid screening Fourier transform infrared spectroscopy. It's a mouthful, so I'll call it FTIR. And this was for looking at herbs and spices in authenticity. It's, again, a non-targeted method, and none of the official laboratories had FTIR. So we used our laboratory grant funding to enable the transfer of this technology into one of the official labs. And this is currently happening. And also at the same time, we've been working with DEFRA on next generation sequencing to genetically screen herbs and spices. And this work is also a currently ongoing piece of work as well. So the second case study is, it's a joint sort of collaboration between DEFRA and FSA on the review of methods for the verification of country of origin. Now, origin testing has always been very challenging due to complex global supply chain, environmental factors, and mainly the limitation of analytical methods as well. So through our sort of intel surveillance, we identified again another gap in knowledge of for testing methods to verify origin. And we commissioned literature review and a stakeholder engagement work with Ferroscience, who conducted the work for us. And I'm not going to say too much about it because I know we've got Helen Grundy, our project lead at Ferra, who will go into this project. And it's a really sort of exciting project. So be around to listen to her talk. The report has been published and has helped us to respond to many inquiries we've had on country of origin, as well as it will help us inform future sampling and surveillance in this area. And then we don't just look at analytical methods, we also look at assurance approaches as well. And there are two sort of really good examples of assurance approaches that we've used. And these are actually a collaboration between FSA and DEFRA over a number of years. So I think Gideon has already mentioned the first one, which was the publication of the first standard of its kind for horse meat speciation. Again, this was done under DEFRA and FSA funding and was conducted by Laboratory of Government Chemists. It's such a pioneering method, and it's really quite good for UK to have done this because it paves the way for other sort of standardization activities for meat speciation. We have got a follow-on method, part 2, which is on processed horse meat and pork meat, which we hope to take through standardization in the future. And the second assurance project that we did was on the point of contact validation guidance. And this refers to guidelines for verifying the accuracy and the reliability of rapid testing technologies using point of contact devices. Now, these point of contact devices are on-site devices which can be used along the food supply chain rather than in the laboratory setting. So there's a lot of, you have to be, important to get the validation correct, because you've probably got non-analysts using the devices. And so it's I think this sort of project was really important to get done first before we start looking at, closely looking at all the devices. So the initial review was done by LGC, and obviously we funded the project. But yeah, it's quite exciting what the work that we're doing. So hopefully these examples can show that through our committed work and shared goals, we can help tackle food fraud, protect the consumers, and safeguard the integrity of the UK supply chain. And also at the FSA, we're excited about the ongoing advancement of authenticity research, and we look forward to hearing all the talks in the conference. So thank you very much, and I'll pass you back to Sophie.
I'll be very quick because I know we're at time now.
So 1 minute.
I'm just going to show this slide quickly, which was it was a workshop we did with our expert committees last year to look at some of the future drivers impacting on food fraud. And I won't go through them because I think everyone's very familiar with the sort of issues that are impacting on supply chains and potentially then on fraud and authenticity, geopolitical instability, increased costs for food production, climate change impacts, that kind of thing, which I think sort of leads on to some of the technical and scientific challenges that we asked the workshop to look at as well. And I think my main sort of takeaway from that workshop and from the slide here is that increasingly we're going to need tools that are very flexible, that can look at lots of different issues simultaneously, that are able to use platforms that are already available given resource pressures that we have on food sampling and laboratory capability as well. Ideally, we want tools to be cheaper and more efficient, quick to run but still robust. And I think there are some areas where there will be opportunities to better ensure food authenticity in the future around things like data handling and storage and technological advancements in methods, artificial intelligence, and I suppose reducing costs for some of the high-tech applications as well ultimately might open up opportunities for future testing tools. So I was just say thank you very much for listening, and I'll hand back to the chair. Thank you.
Lovely. Thank you very much indeed, Bhavna and Sophie, for setting the bar so high for to kick off our presentations this afternoon. Most enlightening. So thank you very much indeed, and very exciting too to hear about the work you're doing. So now it's my opportunity to introduce Kate Helmsley. She'll be talking to us about best practices in building databases with machine learning to support food authenticity, which I'm really looking forward to hearing about. Kate leads on the Centre of Expertise on Food Authenticity at the University of East Anglia. So over to you, Kate, and welcome.
Thank you very much. Can you hear me?
We can, yes.
I'm trying to share, but nothing's happening. Why not? Try again. There we go. Maybe. Can you see my screen?
Yes, I can see
Excellent.
your slides.
Good. That's good. Let me start this going. Move that out of the
Can you
way.
get them to help? Kate, I think you might need to change which mode you're presenting in.
I'm in side by side. Is that not the right one?
I think it's just a bit small.
Is it?
Yeah.
Oh. How do I do that? Unshare and try again.
Yeah.
Stop sharing. Share.
Yeah.
I've got content only, stand out, side by side. I did side by side. Is that not right?
I'm not an expert on this, but hopefully our colleagues will be able to advise. But try content or standard,
Content.
or just standard.
Okay, I've got content and screen share. Is that better?
Yeah, that's better.
Excellent. Okay, let me move you out of the way there. Is that good?
That's perfect.
Good for everybody.
Spot on, yeah, perfect.
Get rid of that. There we go. So, well, thank you for the introduction. That probably saves me saying very much. Yes, I'm from the University of East Anglia in Norwich in the UK, and I hold a chair in the Department of Chemistry, Pharmacy and Pharmacology. For most of my career, I've worked on handling the types of data that are obtained from analytical instruments, most often applied to biological samples of various kinds. And in recent years, as computers have got faster, the methods that I've been using have more and more come under the umbrella of AI and machine learning, which is what I'm going to speak about a bit today. So just to give you an overview, come on. There we go. Of what I'm going to cover. So first of all, I'll look at some of the considerations that we need to make when using these methods for authenticating foods, which in terms of a statistical analysis is essentially a classification problem. So we want a test that will tell us whether something is authentic or not. Now, the main consideration I feel that there is that we're dealing with natural products here, which have got a very variable composition. And that's got real implications for how we compile our reference databases. We need lots of samples to cover that natural variation. And actually, that's no bad thing as far as machine learning is concerned, because not only is it ideal for handling large numerical data sets, it actually requires your sample collection or your independent observation collection to be big. I'll draw on some examples from our back catalogue of authenticity issues that we've looked at over the years, and then finish up with a little bit of a summary on my final thoughts on best practice. So to start with, here's a typical authenticity scenario, if there is such a thing really, but this is one that we looked at many years ago, in which we were seeking to classify sulfited fruit purees as either authentic or inauthentic. Now, sulfited fruit purees are what's traded for use in food products that are manufactured from jams through to yogurts and anything that uses basically a fruit content. What they look like, all of them really, is that example there I've got, kind of a brown mush, because the sulfiting does change the colour, and it's very difficult in its raw state to be able to tell the difference between the different sample types. We were focusing on strawberries because it's a high value product, and this can be adulterated in the real world with anything that's locally available and cheaper. So there's actually a much longer list than just plum, apple and cherry, all sorts of other fruits as well. But the key thing in building up our reference collection was to make sure that we had assured provenance and trusted suppliers, as always. And actually, in this case, this involved going round an awful lot of strawberry fields over the summer in various locations to actually collect them ourselves. And that provides us with the clearly defined class, our authentic class. But then for any model development, even if you're using some of the methods that are called one class classification, you still need to at least test your samples with your model with inauthentic samples. So that forms an open-ended class. It's really as whatever you want that's not strawberry in a fruit puree domain. So that's quite a challenge. That's something to bear in mind. So thinking then about natural products and natural variability, really there's all manner of different things depending on the product you're looking at. So in this case, you can think of a few things that might affect natural variability. So I've got a few of them there: seasonality, the cultivar, how they've been looked after harvest. And all of those apply to the inauthentic samples. And I've tried to represent what you're dealing with by the points in each of those circles. They're kind of showing you that as you add in more samples, you'll start getting towards the edge of those classes. And especially with the inauthentic samples, as you start adding in adulterated strawberries, because they're non-authentic as well, you'll end up in this sort of situation. So mixtures. Here's just with plum. As you add more plum, you gradually go over to the plum side. Less plum means you're overlapping with the strawberry side. And that really is quite a challenging issue, but I would say it's quite typical of a lot of authentication scenarios. Not all of them, because sometimes you're dealing with a unique cultivar or a unique species, but very often you're dealing with wanting to detect a small amount of adulterants. So that brings into the thoughts a detection limit consideration that you have to think about quite carefully. And actually in authenticity, we often speak about 1% or perhaps up to 5%, because getting lower than that, we're talking more about contamination levels. And that's really to do with why people might commit fraud in the authenticity scenario rather than just accidental contamination. But anyway, they're kind of considerations that you need to make at the point of building up your reference database and your inauthentic test samples. So really there are two classes of authenticity scenario as well, beyond looking at the authentic versus non-authentic. There's whether we're dealing with a simple marker compound situation or a more general profiling situation. The marker compound, there's no doubt, is easier. You've only got one thing that defines your authentic class. Then you can use classical statistical models, so probability distributions as an example. And this is probably a well-known example, and it's one that we've worked with quite a lot, which is Arabica versus Robusta coffee beans. So there are two commercially grown coffee bean species of note, and Arabica is the high value one that everybody really wants to be able to put on their product labels. Robusta is also commercially grown in large numbers, and it's quite a bit cheaper usually. But very handily, there's a marker compound called 16-O-methyl-caphostol, which is only present in Robusta. It's really pretty much absent, only there at trace levels in Arabica. So if you measure this by whatever method, you'll find that the distribution of Arabica beans is like this over on the left-hand side here. Really not very much at all, beyond about 30 mg per kilo. You get to 50 mg per kilo, and you're really not looking at an Arabica. And because Robusta is so far away down the other side, you've actually got quite a good situation for being able to detect mixtures, because pretty much whatever Robusta bean you choose, when it's down at maybe 1-2% level, it will still pull this over to above the threshold. But not all scenarios at all are like that. And what I'm going to speak about for the rest of my talk today is the profiling approach. So this is when you make a broad screen analytical test, typical of all the kind of instruments that are used in modern instrumental chemistry. So mass spectrometry, infrared, NMR, GCMS, all the various instruments that you'd find in an analytical lab will churn out something that's either a spectrum or a spectrogram or some other profile. And your data set comprises a big stack full of these. So each individual reading has got lots of numbers, and you've got them all stacked together into a matrix. Or you might do some pre-processing and turn that into a table of peak integrals, but nevertheless, you'll still have some sort of width and lots of depth. And when you're in that sort of situation, you really need to handle this type of data with computational statistics. So what do I consider that to be? I would say that's a field that's come about as a result of computers getting really powerful over the last 30 or 40 years. I mean, some computational statistical methods were developed before that, but they weren't used in anger or very widely spread. But there's been an absolute explosion in uptake of these methods, really since the 1990s. Actually, artificial intelligence methods have been around since the 90s. We've used them then, but it's really in the last few years that they've become much more widespread because the computing power does continue still to get better. Maybe starting to plateau a bit, but we're looking ahead to quantum computing coming online as well. So who knows where it's going to end. I would view really computational statistics as the overarching family under which are the machine learning methods. And what they share in common is that they produce probabilistic predictive models. What I mean by that is they incorporate an element of randomness in their inherent workings, and so stochastic behavior, and you end up being able quite often to attach a probability to things at the outcome end, not necessarily at the input. So actually they're quite tolerant of a wide variety of distributions of input, that you don't really make any assumptions about your data when you put them into these complicated models. A lot of them lend themselves to ensembles, and what I mean by that is you make lots of small models or lots of quick models and then pull the output. And then other terms that you may have heard in combination with artificial neural networks are deep learning and convolutional. So deep learning just means huge numbers of weights, lots of layers of weights that have to be decided upon. That's the model coefficients. And then there's convolutional, which is something that's come about maybe in the last 10 years, which is what all the really exciting AI methods that you're now getting in everyday life, so image recognition and large language models, they use convolutional aspects, which increase the number of weights even more. So I'll take a closer look at one, well, typical machine learning method, because it does share some of those properties, and that's random forests. They're very useful, they're very quick to implement, very unassuming in terms of what you can stick in and what you can get out. They leverage randomness, and they need a fast computer to make these big ensembles. So what I mean by that is that each little model, which in the case of random forest is a decision tree, you make lots of them and then take the output from all of them as aggregated as your ultimate prediction that you're trying to make in terms of your test. So breaking that down a little bit, we've got our data over on the left-hand side there. So a stack of authentic and adulterated spectra. The way one model, one decision tree within that forest works is you pick some spectra at random, you pick a few subsets at random and build a decision tree. And you do that by splitting each data point at some value, and you keep doing that until you've got no more splits to make. And then you assign each leaf to whichever has got the most items in it at that stage. And you do this loads of times, and that's your random forest. So I can show that working in practice on one of our authenticity case studies. We worked on this a few years ago in conjunction with a Moroccan Research Institute, which was our trusted supplier of assured provenance argan oils. Now, argan oil is not really known over here as being a food, but in Morocco it is. It's very much, you know, a competitor to olive oil in terms of what people use it for. Over here, it's sold as a cosmetic ingredient, and that demand around the world has meant that Morocco feels that its protected supply, because it's pretty much the only country in the world that produces it, could be under threat. People are just mislabeling stuff and offering them to cosmetic suppliers instead of argan oil and pushing the price down. So it's obviously of interest to them to have a quick screening method. And what we looked at was chemical profiling data. So that was from benchtop NMR. That's one of the fast screening techniques that may well be coming online in years to come. That produces from undiluted oils, you just literally stick some under like 500 mils of argan oil in an NMR tube in the spectrometer, half a mil rather, in a spectrometer, and 5 minutes later you've got a profile looks like this. My argan spectra on here are in red, the other ones are other types, and you see that there are areas which are chemically distinct. And actually in this case, for oil spectra, we can make quite good chemical assignments of some of these things as well. We had a lot. We had hundreds of assured provenance argan and hundreds of assured provenance actually olive, and then mixtures with various other oils with argan. And these were fed into a random forest. So I've got an interface here which shows you the various things that you see when you set one of these going, which is what I'll do on the next slide. There we go, it's setting off. The decision trees that are being used each time is flashing past on the left-hand side. Up the top, we've got the misclassification error rates as a function of the number of trees in the forest. It starts at about 10%, so 10% are wrong in classifying them as either authentic or inauthentic, but as you add more trees into the model, that gets better. Now, sometimes the trees are duff, they're rubbish, so then they make the error overall worse, but the concept of wisdom as crowds is that eventually you'll stabilize on something which is a pretty good estimate of what you can achieve with that data set. And there's no input in terms of interpretation or scaling needed, or it's very, very tolerant of what you might want to stuff in. So in this case, I've literally just put the spectra in, and this is what you get out. And at the end of training, so typically you'll need about 100 or so trees in the forest, you'll end up with substantially better predictive accuracy, down at about 3% instead of 10% compared to just one tree. And what gives you some sort of confidence is that it's actually picking up on real chemical information. Is down the bottom, if you can see it, yeah, if I move my mouse out of the way, you can see that the predictor importance, which is what's shown down the bottom with the variable occurrence, is homing in on the areas where we can see that there is chemical difference between the argan and non-argan oils. So that's random forest. It does pretty well. Actually, in the publication on this, we compared it with some other methods, and it was perfectly good. I wouldn't say it outclassed anything else, but it made a good effort. So the second machine learning type method I'm going to just briefly touch on is artificial neural networks. So this is what's really given rise to the phrase artificial intelligence. And I would say that the sole reason for that is this diagram on the left-hand side. This is a schematic to represent the original neural network, which was a simple feed-forward network, or a multi-layer perceptron is another word for them. And they were always represented like this, where you've got nodes and weights. And these were said to represent or be similar in concept to neurons and synapses. To be honest, I think that's where the similarity ends, because these things are all just numbers and vectors and matrices. And just like the other network, which is represented slightly different on the right-hand side, where we've got the weights now represented as coloured matrices, and we've got a convolutional layer here, which goes round and round with lots of these weights. Both of these can be represented as matrix operations and transfer functions. And in terms of linear algebra, you multiply, you add together, you maybe apply some nonlinearity at some stage in one of the layers between these operations, but you can write them all out in a line of code. It's not magic in some way. The difference between these now, the convolutional neural network, and the very simplest ones as they were first used decades ago, is the huge number of learnable parameters. So we are talking thousands, tens of thousands even. I'm working with a data set which has got millions of observations and thousands of weights. And actually, in getting the solution to that, you need to use an optimization method. It's got non-linearity in it as well. So in order to find the solution, we use what's called gradient descent of the solution landscape. And that actually means that you're trying to find a local minimum. And that again feeds into this idea of lots of learners with not always perfect solutions. And you do it lots of times and aggregate over all the outcomes. And that gives you a robust prediction, or more robust than only doing it once. So how does neural networks fare? So returning to my original example of fruit purees, they were actually a real project. It lasted 3 years. I said we went around and collected lots of certain provenance fruits. About a third of those were pure strawberry. The rest were other fruits and mixtures. And we published our results of that project, which was actually funded by the Minister of Agriculture, Food and Fisheries, so the predecessor of DEFRA. Published it in 1999. That's our data set there. There's actually 1,000 selector or so on there. Loads of them are very, very similar to each other. And actually, it does look like the strawberry are bang in the middle, right on top of most things. So you might think, oh, that doesn't look very promising. But actually, it is. It's quite doable to get a very good classification success rate with this. What we did after our research was finished was place the data set in the public domain. And it's been repeatedly analysed by other researchers many times since then. The most recent one that I could find in the literature was reported in 2020. And actually, they'd used that to compare the performance of lots of deep learning neural network models on it. The actual winner is over on the right-hand side there. It's even more complicated than the diagrams that I'd shown previously. It's got lots of layers. It's got normalization. It's got scaling. It's got convolution. And actually, it does really well. So if you look on the table of classification accuracy, 98.65 is actually pretty good. Couple of percent higher than the multi-layer perceptron, which was next, and substantially better than the others, which are frankly pretty awful, actually, because I know what you can achieve without using neural networks at all, because that's what we published back in the 1990s. And we used basically principal component analysis, a few variations on it, but PCA, I'll just have a final word about this because it's actually so widely used, and in lots of ways I feel it's a kind of baseline method of analysis. It's founded on linear algebra. It actually was proposed in the 1930s, but not really done until probably the 80s because it does actually involve too many calculations. But nevertheless, you can write down all that you need to in terms of algebra in about 3 lines. It's really well described and well founded. It's well established for reducing data complexity. And what I mean by that is you start with your spectra and you decompose it using that algebra into a set of kind of pseudo spectra, the weights, and then some scores. And these are both much, much less complex. There's only a few of them usually that you have to bother looking at than the original data set. So in this case, my scores are there on that 3D axis. And actually the first 3 principal components look like they can do a pretty good job of separating strawberry from non-strawberry.
Now, if you could sum up now, please.
I've got one more slide, I think. You can use these in conjunction with other modelling methods. You do that by placing a boundary around the class. And actually, what you find with this particular example is it's pretty much as good as neural networks. It's certainly as good as traditional neural networks, and only a couple of percent worse than the convolutional neural network. So all is not lost if you don't really want to do an AI method. If you've got too small a data set, you can use linear methods fairly safely. Most analytical data is well handled by those methods. I'd say the pros of machine learning are they make few assumptions and they're capable of modelling very detailed and complex relationships. But the negatives are they require really large numbers of samples and they're computationally expensive. No modelling method's perfect and can't perform miracles. So if you put in rubbish data and you'll get rubbish out. So more important, I think, is real careful consideration of the nature, the quality, the quantity of your reference collection, and of course your analytical measurements. And I'd like to leave you with my acknowledgement slide of the various people who funded this research over the years. Many thanks to them.
Thank you to you too, Kate, for explaining that so expertly. That was fascinating to hear about how AI can help us address the authenticity challenges. So questions in the chat later for Kate, and I'll pick those up at the end of the session. So now it's my pleasure to move on to our next speaker, which is Helen Grundy from Ferroscience. Helen's the science lead for food authenticity, and she's going to talk to us about emerging methods for verifying country of origin, which you've already heard a little bit about already from Gideon Henderson, who touched on it. So very much looking forward to this too. So Helen, over to you, and nice to see you too.
Thank you. Good to see you, Lucy. Thank you to all the organisers as well for inviting me today. It's a real pleasure to be here. And I know it's a great undertaking to organise a conference of this size, so thank you. Can everybody see my slides? Are my slides displaying, Lucy? I can't see you, Lucy, so you'll have to tell me.
Yes, yes,
yeah,
sorry.
Brilliant. Excellent, thank you very much. So yes, I'm here today to talk about methods for determining the country of origin of foods. There we go. This is an area that FAIR have been working in for quite a lot of years, and we're really pleased that the Food Standards Agency and DEFRA funded some work last year for us to review the literature and to engage with stakeholders to review the capability of methods to verify the country of origin of foods and feed. And as has been touched on today already, but for a variety of reasons, products have a protected geographical indication or a protected designated origin, and consumers feel that the characteristics and the quality of foods are worth investing in, and these foods carry a higher value at market. So in the UK particularly, we have various sources of lamb, geographical origins of lamb and beef, clotted cream. Welsh heather honey is another project with a protected geographical indication. And further afield, Parmigiano cheese and lots of olive oils have different protected statuses depending on the region that they're grown in, and also the refining processes. And in America, bourbon whiskey has protection as well. So customers are willing to pay a higher price for these products, but also as well, this is a really important question, I think, as each of the speakers have said today, because traceability in the food chain is critical, the supply chain. To make sure at the end of the day our food is safe as well as being authentic, we mustn't lose track of the traceability of the foods. So to define country of origin, it's the country where food or feed is entirely grown, produced or manufactured, or if it's produced in more than one country where it last underwent a substantial change. And to protect the geographical origin of food is to protect consumers, first of all, who relate the geographical origin to superior quality or brand, or indeed sometimes it's a question of loyalty to a particular area of production, and they're willing to pay a premium price. And at the same time, we're protecting businesses who maybe are monitoring food miles, ensuring the sustainability of their foods, checking them up from deforested areas, for example. Avoiding goods which are subject to sanctions, and reassuring consumers regarding farming and welfare standards, as well at the end of the day of protecting the business's brand and the associated value. So the aims of the project that we undertook for the FSA and DEFRA were to identify the relevant technologies involved in verification of geographical origin. You'll notice I've put verify in apostrophes there. This is because sometimes we're able with technologies to determine the geographical origin and say, yeah, it's from this region. But a lot of the time we have to use a weight of evidence approach, use different technologies which all feed in different pieces of data to give an answer which is indicative of the geographical origin. Sometimes we can say, well, it's definitely not from there. If it's labelled as being from there, it's definitely not from there, but we can't zone in on exactly where it is from, but sometimes we can. So the project also identified challenges and limitations in the methods and also made recommendations to future-proof testing going forward. The first type of analysis that I'd like to go through for geographical origin testing is stable isotope ratio analysis, which I'll call SIRA throughout the presentation. This is perhaps the most used, certainly for ferrets. It's the technology that we use the most often for verifying origin. It works for a lot of commodities. It doesn't work for all of them. It's not the most appropriate for all commodities. And as you'll see during my talk, depending on the commodity, depends on the technologies which are most applicable. But SIRA uses the isotope signals from different bioelements which are present in the local feed and geology and water, and ultimately get transferred to plant tissue and then to animal livestock tissue. We look at the isotope ratio profiles to determine where a food is from. And like all of the methods, or most of the methods that I'm going to talk about today, these are underpinned by databases, so it's really nice. Kate's done a really good job for me to describe the data sets and how they're developed for a lot of these methods. And these databases involve a lot of authentic samples and certified reference materials, and then, as Kate has talked about, modelling of these of the data sets. And just to give an example of how the theory behind some of the stable isotope work, there are stable isotopes of hydrogen, hydrogen and deuterium, which is the heavier version, and also stable isotopes of oxygen. We look at oxygen-16 and then the heavier version, oxygen-18. And these occur naturally in waters and biological materials, and particularly in the ocean. When you get water droplets made with the heavier oxygen or the heavier hydrogen, when these evaporate and form clouds, because these isotopes are heavier, they tend to fall out more quickly. So they precipitate, they rain out of the clouds nearer the coast and also at low altitudes before the clouds move up. So there's a fractionation of these isotopes depending on often coastal region and altitude. We can use this information to feed in when we're working out where a food has been raised. And as I mentioned, there are various isotopes that we look at. So hydrogen and oxygen we look at from the hydrology of an area. We can look at carbon isotope ratios as well. With C3 and C4 plants, the carbon isotopes are fractionated in different ways in C3 and C4 plants. In nitrogen as well, nitrogen levels depend on fertilizer, whether it's a synthetic fertilizer or whether it's a natural manure or organic manure, and again for sulfur and strontium as well. And as I mentioned, for carbon ratios, if it depending on the photosynthetic pathways in a plant, we can look at C3 plants and C4 plants. And C3 plants have lower levels of the carbon-13 compared to the lighter version, and this works out really nicely. It means that we've got methods in this country and parts of Europe. Livestock is fed on wheat and pasture, nice green grass, due to our beautiful weather systems that we have here with plenty of rain. And we can look at different carbon-13 ratios, and in places like America where it's more arid, and Brazil, livestock tends to be fed on feed all of the time, so maize and sugarcane. So this provides methods, as have been mentioned this morning, today, for looking at beef. So this is a nice piece of work on beef where there were 430 livestock samples, many of which were raised on a C3 pasture, plenty of grass, and then moved to a C4 diet, a mixed diet, after 167 days. And then the samples here were raised in America and Brazil on a C4 diet. So we can pick all this up with the isotope ratio mass spectrometer. And at Ferro, we also use these methods to support consumers in their choices of food. Grass-fed beef often carries a premium price, as does corn-fed chicken, and we can use these data to assign whether a meat sample has been fed in a certain way with a certain farming practice. We can also look at sustainable farming. Has a product come from a deforested area? We want to support deforestation-free practices of cattle, soya, oil palm, coffee, cocoa, for example. So as I said, most of the methods that I'm going to speak about today rely heavily on databases and modelling. And databases are only as strong as the data which underpins them. So authentic samples are critical. If you have a database full of olive oils, you need to check that those olive oils are from a certain area and they've been prepared in a certain way to form the basis of your data set. What we found in the literature when we've been reviewing the literature for this project was a lot of databases had been set up, but they were for very small, limited areas. So, for example, there was some work in China where 2 regions were studied, but they were geographically quite remote compared to each other. So a lot of the work in this area is proof of principle work with small data sets to prove that the methodology can be applied. So it'd be really nice in the future to have larger data sets that cover much larger geographical areas. And also data sets need to account for natural variation, seasonal variation and annual variation. So they need to be continuously grown. More data needs to be put on each year, each season. There's examples where methods have worked really well for basmati rice, for example, by trace element methods. They work perfectly one year, and then the next year there'd been so much variation that the samples, the data that came out was pretty mixed up. So we need to keep accounting and keep our databases up to date. Yeah, basically a lot of the work in the public domain, the databases are small, the number of samples in there are less than 200. But another thing that came out of this work was that a lot of data is improved if it's combined with another technique. So a lot of stable isotope ratio analysis data can be combined, for example, with trace element data or sometimes with NMR data. And the combination of techniques adds for a stronger data set and more accurate outcomes. So I'll move on to trace element analysis now, which was the area that was used for the basmati rice example that I just gave. But again, as has been nicely introduced by others, trace elements can be analysed. They come from the environment and they depend on the rock origin of the soil and pH and clay content, climate and human activities as well, fertiliser addition, etc. And these can be measured to determine geographical origin. And as I said, when combined, particularly with stable isotope ratio analysis data, you can get some really strong data. For some commodities, trace element analysis works really well as a standalone method, but often when combined with other analyses, it's improved. So here's a really nice piece of work that we were involved with, again on beef, where you're looking at different isotopes, sulfur, strontium, nitrogen and hydrogen, and rubidium, but also adding in the trace element data here. I don't have a before slide, I've only got the after slide with me today, but really nice separation of the classifications of the data. And if you consider that some of these farms will be geographically pretty close to each other as well, it's a really nice piece of work. Another area that filters in nicely to geographical origin testing is metabolomics and profiling, particularly if you've got a food commodity that isn't working so well for stable isotope ratio analysis or trace element analysis. You can use targeted and non-targeted methods. And with non-targeted methods, there's literally hundreds of biomarkers that you can consider, some of which will be related to climate, geology, feedstuff and fertiliser, which will feed into giving you a picture of where your geographical origin of that product was. If you concentrate maybe on sugars or fatty acids or other volatile compounds. And this also allows really good data access to metadata. You can look at how the processing of the commodity has been undertaken. We've been able to determine if steel has been used during the winemaking process, steel vats, or if wood chips have been used during vinification. So it really adds into the story of geographical origin and production process. And with metabolomics, it's often based on spectroscopy methods. So there's the potential in the future for rapid, portable and affordable non-specialist technologies to be developed handheld, which can be used at point of use in warehouses and what have you. So there'll be less waiting around in the food supply chain to use your ingredients if you can test them at when you've received them. Some niche applications which feed into geographical origin, genomics is one of these. Sometimes you're really lucky in the commodity that you're looking at, and only a particular plant cultivar will provide that product, or it'll only grow in the region where you're growing. It's best suited to that region, and genomics filters in really well here. But genomics also has potential to add value in combination with other approaches. So there's a Chinese cured ham, and there's a really nice method with genomics and metabolomics analysis. And Portuguese wine testing as well works well with genomics testing along with strontium stable isotope analysis. Another niche applications, NMR and GCMS methods work really well for olive oils, looking at the sterols and the fatty acids to determine markers of or fingerprint profiles of their geographical origin. And again, GC and FTNIR and SERA all fit in nicely for geographical origin of palm oil. For honey, spectroscopy methods have been used, NMR, IR and Raman. And for coffee, genomics methods and FTNIR methods are looking very promising as well. All of these methods are very much in their infancy. There isn't a great deal of data out there, some more data than others, but yeah, more work is needed in all of these areas, and that was quite clear from the literature review that we did. Other applications that I'll mention, blockchain's being mentioned today, which is a really fast way of checking your supply chain if you think you've got an issue, rather than sorting through paperwork and trying to source your certificates from different suppliers. And it has been sort of quoted that it increases transparency in the food supply chain, and I think it does to a large extent. It's very expensive to incorporate, especially early in the supply chain, where nations perhaps don't have the same funds as we are lucky enough to have over in the UK and the West. It is very vulnerable to falsification, manual falsification or accidental error. And as I've said, your data sets are only as strong as the initial data, so that's a real risk area, I think, for blockchain. And again, remote sensing, it can be another string to your bow if you're trying to ensure the geographical origin of your food. But again, it's open to manual falsification and error. So this is just a little snapshot from the project, really. There was probably about 4 times the number of commodities shown here, but this is just to give you a snapshot of the most promising technologies for each commodity. Particularly here, this is a very standardized method now, stable isotope analysis and SNP NMR. But a lot of these other methods are definitely areas to look out for that are looking promising in this area. And as part of the project, we did a really interesting consultation with World Forest ID, who are a non-profit organisation set up originally, I think, to work on timber products, to check that timber isn't coming from areas subject to sanctions, but they've spread their remit to all sorts of forest products and other foods as well. And really speaking about a model way to go about geographical origin testing. So they combine, as we often do, stable isotope ratio analysis and trace element analysis. The two go really nicely hand in hand and complement each other and strengthen the data for each other. And they advocate for a large curated database, which is really important. You want control of your database. You want it to be large. You want it to span a large geographical area, but at the same time, you need to have control of the data that goes in there. So you need authentic reference samples. So what World Forest ID do is they train personnel all over the world to go out and source them by hand, authentic samples. And those are the samples that are tested by SERA and trace element analysis. And that data is fed into their databases. So they've got full control. And all of the labs, well, there aren't many labs involved, but the labs that are involved are trained to a certain standard. They're into laboratory trials to check that everybody's data is harmonized. And at the end of the day, this data becomes accessible to the public, which is really nice as well. And you've got transparency of the data that's being used in judicial cases. Yeah, so we use that as a model of how to manage your databases during the project. Increasingly, these methods that are used for food origin determination, geographical determination, can be used to support sustainable sourcing of food and packaging. The EU have got their new deforestation-free regulations, which cover soy, palm oil, coffee, cattle, and cocoa, and also timber and rubber. What's really important for us in food testing, I guess, is that there's all of those foods to consider, but also your packaging. So pallets, making sure that your pallets come from sustainable timber if you're trading with the UK, with the EU. And the UK has intention at some point, I think, there's definitely been discussion in the UK to have similar regulations. I think they're on hold after the general election. But yes, for anybody interested in that area, we're holding a webinar with the FDF next week as well to discuss our services in that area. So please join us if you're interested to do so. The challenges and the limitations and the recommendations that we found from the project the challenges were curation of authentic samples. There's a real problem that data sets are built on samples that are just sourced from a shop. So they may be authentic, you hope they are, you look at the label, you do your best to source from those that you consider to be reliable sources, but at the end of the day, it's ideal to go to growers, to livestock farmers, and get your samples direct, or to make your own olive oils, to get your seeds, and to have management of the refining process so that your samples are authentic. And as I said, a lot of the maturity of the studies differs a great deal. So there was a lot of proof of principle studies discussed in the literature, and not many mature studies out there. There is also very little engagement in proficiency testing, and it would be really good in the future if there could be more proficiency testing in this area to standardise methods and to give confidence in methods. And as I've said, the databases are often too small and not based on authentic samples. So our recommendations were to get more standardisation of samples, to have a curated database, a coordinated approach, and to invest in certified reference materials which are needed to standardise your methods as well. And to have databases that cover a large geographical scope. So if we're called on in a food emergency, you know, the databases are there, you can build them up, but it would be nice to be able to just start work straight away. And these databases need to be challenged and continuously updated. And also in the future to invest in low-cost technologies that could be used for screening, so point-of-use work. So I've touched on that already, most likely with spectroscopy technologies. For anybody interested, that's the project report. Final report can be found there and scanned. The QR code will take you directly to it. And again, thank you to DEFRA and the Food Standards Agency for funding that work, and for all the different parties who have funded some of the work that I've spoken about today. And the specialists and stakeholders who were involved in the project, really grateful to you, and gain a lot of knowledge speaking to you all. So thank you very much. And some of the work that I've spoken about was funded by Food Integrity and Trace, and various parties were involved in some of the work that I've spoken about, beef, along with FERA. So I'll leave you with a picture of FERA on a sunnier day than this, and thank you, and I look forward to the questions later.
Helen, thank you very much indeed. It was absolutely fascinating to hear about the journey through the work that FERA has done on country of origin, some of which I know very well. So it was very nice to hear about that again. So before we move into a break, I just wanted to remind you to continue to submit your questions for the speakers, which we'll cover at the end of the afternoon in the Q&A channel during the break. And also to put a question to you, we'd love to get your thoughts on this particular question: how might emerging and future technologies help combat food fraud? So the question is, how might emerging and future food technologies help combat food fraud? So please click on the link in the chat and leave your thoughts and comments on the interactive whiteboard. And we'll see you back here now at 15:05. So now we've got a 15-minute break. Do come back at 15:05. Thank you very much.